Hello and welcome to this week's edition of HoloTube. Glad you all could tune in for David Mateos' talk today. We are very happy to have you, David. The screen is yours.
Thank you very much. Thanks for having me. Let me see if I can share my screen. There we go. Okay, so I trust that you can all see my screen now.
Yes, we can.
Okay, good. Okay, so again, thanks for having me. I'm going to be talking to you about something new that I've been doing very recently and that I'm very excited about. And this is based on work done with a number of amazing collaborators here. Without them, there's no way this could have been possible. And in particular, this fall, you should pay attention to these two students, Thanasis and Mikkel, who are going to be graduating and applying for postdocs. So the plan is the following. I'm going to start with a somewhat lengthy motivation, because I think it's important to put things into context. Then I'll describe the holographic model that I'm going to use. After that, I'm going to talk to you about dynamics of phase separation first, because as you will see, bubbles are similar to phase separation, but more dynamical. Then I'll talk about bubble dynamics, and I'll conclude with some outlook. So you all know that first order phase transitions happen everywhere in nature. For example, when you boil water, and the way they proceed is via the nucleation of bubbles of the preferred phase inside the disfavored phase. So you may wonder whether the same thing happens in particle physics, whether there are first order phase transitions in quantum field theories that we know about and that describe nature. If that were the case, this would be very exciting because it would mean that the universe, as it expanded from a very hot state to a cold state as today, would have undergone this phase transition. And this would have probably resulted in the production of gravitational waves because the bubbles that nucleate subsequently expand and collide and have all sorts of interesting dynamics. And that can lead to the production of gravitational waves. And these gravitational waves could be observable in the future, for example, at LISA. So the first place you may look at in order to see if this could have happened in the history of the universe is within the standard model, is in quantum chromodynamics, because you know that there is a transition between the hadronic phase at low temperature and the quark-gluon plasma at high temperature. Unfortunately, we know now, I think, very robustly that this is actually a crossover. It's a continuous and smooth crossover, not a first order phase transition. So the next place that you might look at is the electroweak transition, okay, where the Higgs condenses. But this is also believed to be a crossover. However, it turns out that even minimal extensions on the standard model do have first order phase transitions. There are several models of this type. And that's not the only scenario where first order phase transitions appear. There are two more, at least, that I want to mention. One is that, in these extensions of the standard model, you're thinking of some theory that completes the standard model at a scale that is not too far from the electroweak scale. But you can also imagine that there's some grand unified theory at a scale which is much higher than the electroweak scale, say 10 to the 16 GeV or some other high energy scale, where you have some non-Abelian gauge theory that could have its own phase transitions, which could be first order, and this could give rise to gravitational waves. And the other scenario is that, of course, we know that dark matter is weakly interacting with the standard model, but some people have speculated with the possibility that it's strongly self-interacting with itself. Okay, and if that's the case, then the dark matter sector could also undergo first order phase transitions that could leave an imprint in the form of gravitational waves. So if you're a pessimist, this is very disappointing because it means that we won't be able to study the QCD transition or crossover or the electroweak transition with gravitational waves coming from cosmology. But if you're an optimist, this is absolutely great because it means that any discovery of gravitational waves coming from a cosmological phase transition would be the discovery of physics beyond the standard model. And that I think is very exciting. And not only that, but in fact, in some cases, these gravitational waves produced in this phase transition might be our only window into such physics if the energy that's involved is sufficiently high. So if you want to maximize the discovery potential, that requires an accurate calculation, as accurate as possible, of the gravitational wave spectrum that would be produced in these first order phase transitions. And this in turn requires the calculation of several properties of the phase transition in whichever the theory that you're looking at is. These properties include, for example, the equation of state and the critical temperature, the nucleation temperature for the bubbles, the strength of the transition, like the latent heat, the transition rate, etc. These properties I just mentioned are all equilibrium properties. But there's another property that you need, which is the wall velocity of the bubble. Once you form the bubble, if it's sufficiently big, it will expand with some velocity, and you need to know that velocity in order to compute the gravitational wave spectrum. Now, this bubble wall velocity turns out to be actually the most challenging to compute, and the reason is that this is an out of equilibrium property. Because once the bubble wall is expanding, there's some friction in the medium outside, in the disfavored phase, that gets heated as the wall expands, and so on and so forth, and this is all out of equilibrium physics, and as we know, out of equilibrium physics is much harder to compute or to understand than equilibrium physics. So this is challenging even in weakly coupled theories. But it turns out that not only this is the most challenging parameter to compute, but in fact, it's very pressing, because the gravitational wave signal is extremely sensitive to this velocity. It's more sensitive to V than to some of the other parameters. So what I would like to do in this talk is to explain how to use holography to compute this bubble wall velocity in strongly coupled gauge theories that have a gravity dual. So what I'm going to do is to assume that some bubble has been nucleated. I'm not going to describe the nucleation process. I will assume it's been nucleated with some properties that I will explain. And then I will determine all the subsequent dynamics of the bubble using holography. Now, for simplicity in this talk, I'm going to restrict myself to planar bubbles as opposed to spherical bubbles. This means that the bubbles that I will look at are translationally invariant along two directions, x and y, which I will refer to as transverse directions. And they will expand along some longitudinal direction that I will call z. So all the dynamics will take place along this direction. So just to put this into context, I want to emphasize that this is just a first work in a long-term program. And that's why I'm restricting myself to a very simple case. Also, since we don't know what lies beyond the standard model, I'm going to choose the simplest possible model in which I can do these calculations. And I will try to focus on universal features, which may be robust to apply to a general class of models. Now, everything that I'm going to tell you today is not published. Well, not everything, sorry. Everything to do with the bubbles is not published. And that means that it's preliminary. And in particular, some of the plots I will show you may change a little bit. But I was just too excited not to show them to you. But please keep in mind that this is preliminary, it's not published, and things are not completely settled. Or some small aspects are not completely settled yet. But I think the general picture is quite clear. Also, for this reason, if you have any questions or feedback or criticism, that is more than welcome. So please interrupt me anytime to make comments or ask questions or criticize what I'm saying. So having said that, are there any questions at this point? Okay. So let me talk about holography and the model that I'm going to be using. So in a slide, holography is the statement that there's an equivalence, an exact equivalence between some, let's say, four-dimensional gauge, non-Abelian gauge theory, living in Minkowski spacetime in 4 dimensions, and string theory in some 5-dimensional spacetime, which is asymptotically anti-de Sitter 5. And you can think of the boundary of anti-de Sitter 5 as Minkowski space, where the field theory, the quantum field theory resides. And of course, you all know that string theory in some limit reduces to gravity, in fact, to classical gravity, and that's the limit that I'm going to be working in. Okay, so for practical purposes, during this talk, this is an equivalence between some fully quantum mechanical non-Abelian gauge theory in 4 dimensions and classical gravity in 5 dimensions. So this means that in particular, if you nucleate a bubble, all the subsequent fully fledged quantum mechanical bubble expansion, all the dynamics involved in the bubble and the medium surrounding it, etc., all of that is captured by some classical gravitational theory in 5 dimensions. And in fact, the expansion of the bubble corresponds in that classical theory to the expansion of some black hole horizon. And this means that the strategy we're going to follow, since we don't know how to analyze from first principles this theory in this out of equilibrium situation, in particular strong coupling, instead of that, we're going to solve this problem over here, which is equivalent, by solving or evolving in time Einstein's equations starting from some initial state, dual to the bubble. And then once we have the solution here, we'll simply apply the dictionary and read off the exact behavior of the stress energy tensor in this theory. And that will tell us in particular what the bubble velocity, what the wall velocity is. It will tell us much more than that, but in particular what the wall velocity is. So that's the strategy. Are there any questions? Okay. So the model that I'm going to be using is the simplest model, or one of the simplest models you could think of, which is simply gravity in 5 dimensions, okay? This is the Einstein-Hilbert term, coupled to a scalar field with an appropriate potential that encodes all the properties of the gauge theory. So changing this potential or specifying this potential is the gravity analog of specifying the gauge theory Lagrangian, if you want, the dual gauge theory Lagrangian. And I'm going to choose this potential. This is simply for technical convenience. There's nothing fundamental about this. Just for technical convenience, I'm going to assume that this potential can be derived from a simpler function, which is called a superpotential, this W, through this usual formula. And I'm going to choose W to have this polynomial form. It's a polynomial of order 6 with 2 free parameters, phi m and phi q. These 2 terms are fixed by some conditions that is nice to impose, and these 2 are the free parameters. This is a picture of this superpotential. It has a maximum here and a minimum here. And like I said, the choice for this potential is simply, which Iago and myself introduced some time ago, is simply that this is the simplest model I know that describes a gauge theory that is non-conformal, and such that the gravity solutions, dual to thermal states in that gauge theory, are regular and remain regular. So they are regular at all temperatures and remain regular even in the limit t going to 0. This is just a desirable feature. It's not indispensable, but it's something that's nice to impose, and this is a simple potential that realizes that. So this specifies my 5-dimensional model, and once I have specified this model and I have chosen the potential, there's nothing else, essentially, that I'm free to choose. Everything else is determined dynamically. The only thing I can choose are initial conditions for the states that I want to evolve. Any questions? Okay, so I'm going to be working with different values of these parameters. Let me make a couple of comments before I dive in. One is that, like I was emphasizing, the theory that I'm interested in describing is a non-conformal theory, because in particular, I wanted to have a first order phase transition. So the theory has a characteristic scale lambda, You can think of lambda in QCD, this would be lambda QCD, for example. And the transition in the gauge theory as a function of temperature depends on the values of these parameters here, phi m and phi q. So as you change those parameters, you change the potential, and that changes the gauge theory. And you can go from a gauge theory that has a first order phase transition, as you see here, and plot in energy density as a function of temperature. And you see that the energy density is multi-valued as a function of temperature, as you expect for a first order phase transition, which in this case would happen between this state and this state. But if you vary those parameters, you can actually turn the first order phase transition into a second order phase transition or into a crossover. But in all cases, the critical temperature, either here, or the characteristic temperature at which the crossover takes place, is set in magnitude, in order of magnitude, by this characteristic scale of the theory, lambda. Okay. Any questions? Okay, so let me talk about phase separation. So now I'm going to restrict myself for just a little while to a specific model that has phi m equal 2.3 and phi q going to infinity. What this means is that in this potential, I'm dropping this term. So I'm taking a limit in which this term is absent. So I'm just taking this part of the potential with phi m equal to 2.3. This is one choice that gives you a first order phase transition that I'm interested in studying. Later on, I will change these values and I will choose other values that are more convenient, but that will still give a first order phase transition when I study bubble dynamics. So here's the phase diagram again for these particular values. You see the multi-valued nature of the energy density as a function of temperature. This is the critical temperature. And here in green, you see the absolutely stable thermodynamic phases or branches. In blue, here and here, you have the metastable branches where the specific heat is still positive, but this is not the absolute minimum of the free energy. The theory would prefer to be here. And then in red is what's called the Spinodal region, where the specific heat is negative, and all these states are actually locally thermodynamically unstable. And here what I'm plotting is the speed of sound squared, also as a function of temperature. So what you see is that on the green and blue branches, this is positive. The speed of sound is positive. But on the red branch, which is the thermodynamically unstable branch, the speed of sound squared is negative. What this means is that not only these states here are thermodynamically unstable, but they are also dynamically unstable because the speed of sound squared is negative. So if you prepare your system in a homogeneous infinite state in this, at one of these energy densities, and you perturb it slightly, there is a sound mode that will grow exponentially and take you away from the homogeneous state. So let me show you how that happens. So what I'm showing you here is the energy density in a simulation as a function of time and position, in which at t equals 0 at the back, we start with a homogeneous state in the unstable branch. And we add a tiny, tiny perturbation, which you cannot even see on this scale. Actually, numerical noise is enough. And we simply follow the evolution of the system using holography. So doing this evolution in the field theory would require doing out of equilibrium, time-dependent evolution in a strongly coupled quantum field theory, and we don't know how to do that. But we can map the problem to the gravity side and simply evolve in time Einstein's equations and find the solution, and then go back to the gauge theory and plot the energy density as a function of time and space. And what you see is what you expect, which is that at the very back, at some point, this exponential growth of the unstable mode kicks in, and you go from the homogeneous state to something very complicated here, which evolves in time, but eventually settles down to what you would expect, which is a phase-separated configuration. Okay? The point is that if you start in any energy density in here, that state is unstable, so it wants to phase-separate into something with this energy density in one region, one semi-infinite region, and something else with this energy density at some in the other semi-infinite region. So you end up with a phase coexistence state, as you see here. Are there any questions about this? Carlos, if you're asking, you're muted.
Sorry, I hit the wrong button. So my question is, if at the end the temperature is the same everywhere?
Yes, indeed. If you compute the temperature here, even though the energy density is changing, the temperature is equal to Tc everywhere here, as you would expect from coexistence of phases. That's simply because for the two phases to coexist, you need to have the same pressure or the same free energy on both sides, and that happens exactly at Tc here.
Mm-hmm. And the region between the two phases is going along the unstable branches, or is off, let's say, it doesn't show in the previous diagram.
So this, if you plot the energy density, this energy density, as I will show you, actually, let me show you, let me come back to this in just half a minute.
Okay.
Yeah.
David, just as a follow-up question, how do you compute the temperature? Sorry if you said that already and I missed it.
You compute the temperature from the surface gravity. So this is the gauge theory observable, but this you obtain by following evolving Einstein's equations from here to here in the bulk. So you start with a homogeneous horizon that you perturb. This splits into one high energy horizon and one low energy horizon. And then if you compute the surface gravity, you see that it's constant all along the horizon from here to here to here, despite the fact that the energy density is changing.
But the field theory doesn't know yet about the changes of the size of the horizon, right? Because your horizon is changing over time, and it cannot, like that information cannot travel fast.
It takes some time. So what I'm doing here is, so indeed, you start back here at t equals 0, you perturb it, you follow the evolution, and of course in the bulk, and also in the gauge theory, you're following some out of equilibrium dynamics, until at very late times, you settle down to something that becomes in equilibrium again. But it's no longer a homogeneous state, it's now a phase-separated equilibrium state.
Thank you.
Yeah, no problem. So coming back to Carlos's question, one thing that I want to show you is that this interface here between the low energy phase and the high energy phase, this interface is a property of the theory. It does not depend on initial conditions, okay? As you might, and this actually is expected on general grounds. So to show you that, what I'm showing you on the left here is this phase-separated configuration for different initial conditions. And of course, if you change the initial conditions, in particular the total energy, you will end up with a phase-separated state in which the size of the high energy phase or region and the size of the low energy region are different. But now if you take any of these curves and you shift it by a constant, as I've done here on the right, you see that all these different interfaces fall right on top of each other. Okay? This shows that the interface profile is a universal property. It's only a property of the theory. It does not depend on initial conditions or anything else.
Sorry, so when you say initial conditions and you talk about the GR part, is that different phi scalar field or different, like in which side do you put the initial conditions? Are you, in all these lines, are you varying phi or?
So you can vary everything that you can think of, except for the theory. And that you can do either on the gauge theory or on the gravity side because they are equivalent. But of course, I only know how to solve the dynamics on the gravity side. So on the gravity side, what you can do, for example, is to start here. You can start with an energy density here or here or here or here, okay? that's not going to change the final interface. It will only change how much energy you put in one phase and in the other, because the total energy is conserved. Okay. Or you could, for example, change, you don't even have to start with a homogeneous state. You could start with something that's quite perturbed. Or also something that I haven't explained is that just specifying the energy density in the gauge theory does not specify the initial state at all. You need to specify, in a quantum field theory, specifying the initial state means specifying the expectation values of every possible local or non-local gauge invariant operator in that state. And that's an infinite number of correlation functions you need to specify. If you specify the energy density, you're only specifying the 1-point function. So on the gravity side, you can change, there's a functional freedom in specifying the initial metric on your initial slice, okay? And on that metric, the only thing you're keeping constant when you fix the energy is the fall of near the boundary, okay? So you can change all of those things, and you will always end up with a configuration like this, okay, where the only thing that will change is the size of this relative to that. And this interface will always, always, always be the same. Any other questions?
Can I ask a question?
Yeah, of course. Who am I talking to?
Hassan.
Okay, go ahead.
Yeah. So is like in this plot, what you show is always like a single bubble.
Yes.
At least in these ones. Is there any reason for that? That at the end we will have one single bubble? Or?
Yes, of course there is. Yes, 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 yes. Yes, absolutely. In fact, even if you end up with multiple bubbles because you fine-tune the initial conditions, that configuration is unstable towards the formation of a single. So the minimum, so let me explain this. So if you're in any of these branches, okay, here, here, the preferred low energy, and you fix the total energy in the box. This is important. You fix the total energy, okay, which is what you do when you do dynamical evolution. If you fix the total energy, then the lowest free energy state in those branches, except in the red one, is a homogeneous state with the corresponding energy density, okay? However, if you're here, then this is not the lowest energy state, the lowest free, sorry. When I'm talking about fixing the total energy, to be more precise, I should be talking about the total entropy, okay? So that the maximum entropy state here is a homogeneous state. In here, the maximum entropy state is not a homogeneous state. It's a phase-separated state. And if you have multiple bubbles, that doesn't maximize yet the total entropy. You can show that, okay? The total entropy is maximized by having just one phase here and one phase here, not multiple ones.
Okay, thanks, yeah.
Yeah. Any other questions? Okay. So if I wanted to describe this full evolution in detail, as we did in the paper, that would take an entire talk in itself. So I'm not going to do that, but I'm going to point out one thing that is very important when that will be very important when we talk about bubbles, which is what part of this dynamics, okay, is well described by hydrodynamics. And the answer to that is, in this case, everything, the entire space-time evolution is well described by hydrodynamics, provided you use second-order hydrodynamics. Okay, let me explain this and show you a few plots to convince you. So, of course, by second-order hydrodynamics, I mean the ideal term plus first-order viscous hydrodynamics plus all possible second-order terms. You're probably used to these ones. Of course, you've seen this one many times. You're probably used to this one because here's where the bulk and the shear viscosities would enter. And what I'm saying is that if you want to have a good description of this system, it is indispensable. It's not an option. It's not a matter of improving the description a little bit better, a little bit more. It is indispensable to include these terms. Now, before I show you the plots, let me just say that if I really wanted to be precise about what terms you should include here, okay, that would take a little bit of time, and I don't have time to do that. It's actually a very important point, but I don't have to do that. So let me just refer to these as second-order terms. If you ask me at the end, I can explain it. So these plots here show the transverse and the longitudinal pressure in this system, here shown as a function of z in the phase-separated late time configuration. Okay, so here I'm taking a snapshot at very, very late times in which you have already formed this interface. And I'm showing you the pressures that come out of the gravity calculation. This is the continuous line, so that's the exact result. And on top of that, I'm showing you the prediction from second order hydrodynamics. And you see it's spot on. And here I'm showing you the same pressures, but now as a function of time for a particular value of Z. So I'm taking a slice at constant Z, and I'm showing you the time evolution of these pressures until they settle down to the final equilibrium value at that particular value of Z. And again, you see that the time, not only the space dependence, but also the time evolution is well described by second order hydrodynamics. However, if you try to do this with ideal hydrodynamics or with ideal plus first order hydrodynamics, which is the blue curve, green curve and blue curve, you see that they do not agree with the exact result. They fail miserably here, and they also fail in the time evolution. Okay? This is something that you should have expected from first principles. And the reason is that, at least in the phase-separated configuration, you know that that's an equilibrium time-independent configuration. So all the velocities are zero. And that means that here, all these terms, which are proportional to the velocity or gradients of the velocity, vanish identically. And that's why here the blue curve and the green curve are on top of one another. There's no difference between ideal and first order hydro because the velocity is zero. Okay? And you know that ideal hydro, which is simply applying the equation of state pointwise, cannot describe the phase-separated configuration. So it was bound to fail here. And what is actually remarkable, in my opinion, is that second order hydro does such a good job. And that's because second order gradients, spatial gradients, in the interface, what is really important are the second order gradients here in space. Okay, because you're interpolating between a very high energy density and a very low energy density, and the second order spatial gradients are very large here. So you need to include them if you want hydrodynamics to give you a good description of the interface. I'm emphasizing all of this because this interface, in the case of a bubble, becomes the wall, the bubble wall. Good. So this is everything I wanted to say about the phase-separated configurations. Are there any questions before I move on to bubbles?
Yeah, I have a question, if I can put one at this point. It's surprising that like me, I'm surprised that second order is so accurate, because if the second order gradients are large, what about the third and fourth?
Absolutely. That is related. Thank you, Mark, for the question. That is related to what I didn't explain here. Okay, the point is that so this second order formulation, let me give you an answer in a nutshell, and I can expand at the end if you want. The point is that there's an ambiguity in what you mean by hydrodynamics at any order, because at the end of the day, this is an effective theory. And you know that in an effective theory, you can replace some terms by other terms of the same order, which differ only by higher order terms. So the point is that you need to understand what physically are the important terms. So if you use the usual formulation that is used for second order hydro in evolution codes, you will fail miserably. Okay, and I have plots about that at the end, because that formulation has some time-like gradients here. And what's important in the interface are the spatial gradients. So you need to make sure you include all the spatial gradients. Now, that still doesn't explain why higher order spatial gradients do not matter. But I think the answer to that is that this truncation here is an optimal truncation, in the sense that it's a resummation of all the important terms. Now, why that happens, I don't have a first principle reason for. I can tell you my take on this story at the end, but the natural answer is that provided you include the important ones here, they capture all the physics that's relevant.
Thanks.
Yeah. Any other questions?
David, can I ask?
Yes.
So in your domain wall in this connection between the low and high energy, is it like a symmetric, or it's not really? Like if I look at that carefully.
Symmetric with respect to what?
Like the part which connects to the low energy and the part which connects to the high energy.
I don't think it has to be.
Okay.
I don't see any fundamental reason why it should be.
But you said that like the shape should be a characteristic feature of the theory.
Yes.
Is there any way to understand that? Like how we can characterize it?
Yes, one way to think about this. In fact, if you talk to chemists who work with, for example, metal alloys or chemical mixtures and things like this, where they mix things, okay, like we are mixing two phases here, they know that you can determine to some approximation, this is important, to some approximation, you can determine this curve by requiring that it minimizes some free energy functional, not just some free energy. Okay, so you need to extend your definition of free energy to inhomogeneous states. And you can do that. And in fact, hydrodynamics at second order is doing that for you. Okay, when you determine this curve by solving these equations, in a way, that should be equivalent to minimizing a functional free energy, which is a functional of this curve, of this profile, in which this functional is expanded only up to second order in derivatives. So the theory is trying to minimize or find a thermodynamically preferred configuration because you're forcing it, you're frustrating it because you're forcing it to be here on one side and here on the other. And then it wants to go from one to the other in the way that takes the least amount of free energy, so to speak. I don't know if free energy is really the appropriate concept because free energy is really defined for homogeneous states, but you get the idea. And that's exactly what chemists do, by the way. They determine the interface between, water and oil, if you want, when you put them together by doing some sort of derivative expansion of the free energy of the system.
Isn't this much closer to boiling water?
Who am I talking to, sir?
Steam is low density, water is high density. It's all beautifully hydrodynamical, so they should apply then to what you see when you see water boiling in a teapot.
Well, this depends. I'm not claiming, I don't want to claim that second order hydrodynamics will describe these curves in any theory. This depends on the model, okay? Just like hydrodynamics may describe some systems very well and some of the systems not so well.
Yeah, but I guess with this kind of scalar field, it's really about the density difference, right, between the two phases. Ain't that the case?
So the density difference is important, but there's more than the density difference because.
Are you sure?
Yes, I am because.
Scalar, right? It's
because
boundary you have a real scalar field.
The real scalar field is on the gravity side. I'm talking about
the boundary then.
Sorry.
What is it in the boundary? I mean, you make a whole story. You want to know what the theory in the boundary is, and I want to know what the symmetry is.
Yes, the scalar field is dual to a scalar operator in the boundary theory. So let me go back here.
Typically densities, like an Ising model, blah, blah, right? And then you start to think water, steam, typically. I mean, there are lots of these kind of boiling transitions in any fluid. And you can wonder, right? It may be correct when the interface is really about there should be a UV scale, and when the width of your interface gets off that order, then you have to worry about higher order gradients.
No. The interface
is more mystical than it is. This is very straightforward, simple business.
Okay, so I'm glad you think so, but let me just say that the width of the interface is not determined by a UV parameter. Okay, it's determined.
When the gradients are tiny as compared to any UV scale, you don't have to worry about higher order gradients. I mean, there isn't that principle.
No, the applicability of hydrodynamics So actually, since you say this, let me show you why this is not so trivial as you think. So here, these gradients, in fact, in this description, okay, you can easily check that the second order terms, these second order terms, are as large, literally as large, as the ideal terms. Okay, so in that situation, if you think in usual terms in effective field theory, you would say this cannot work, because effective field theory will break down when my first gradient correction is as large as the ideal term. Okay, and that's not happening.
Right, so I again have a simple question. Why isn't this then not the case in water? You're talking about generic right, phase separation.
I don't know if it is the case in water. I have no idea.
Yeah, but water is a real life example of it, you know.
That's
and
fine. That's fine.
You then say I do it holographically, blah 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 blah.
We should ask someone who does experiments with water. I don't know.
Make any universal statement about it. Likely that, you know, primordial phase transition may be quite like cooking water. Why should it be different? Why should you do anything?
No, I'm not. You keep. I feel that you keep putting words in my mouth. I am not saying.
No.
Can I finish, please?
No. It's about getting carried away by holographic construction, and the question is whether they are universal, whether this is universal physics, and when it doesn't apply to water boiling into steam.
Okay, so
you basically make a statement. No, it's sort of a special case. And
can I answer your question? Okay, thanks. So I'm not saying that this is universal. First of all, I'm not claiming that. What I'm claiming is that for this theory, where I can check, because I have an exact calculation coming from holography, and I can compare to hydro, in this theory, I can claim that this happens. Whether this happens in other theories or in water, I don't know, and I'm not making any claims about that. Okay. That's my statement. Okay. Any other questions? Okay, so let me move to bubbles, because otherwise I won't get to that. So now I'm going to take just different values of these parameters simply for technical convenience. And what I'm going to do is the following thing. So here's again the phase diagram with the first order phase transition at this critical temperature. What I want to do is to prepare a state. So imagine that the universe is cooling down on the stable branch and you enter the metastable branch. And eventually at some temperature, which corresponds to this point A, which could be here, 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 anywhere here, you nucleate a bubble of the preferred phase, which could have the same temperature. Okay, that's what's usually considered. But on the gravity side, you can actually consider that or just a different initial state. So what I'm saying is that outside the bubble here, I'm going to assume that I have the state A with this energy density. And inside the bubble, I'm going to have some other state on the lower branch, which could be at the same temperature or just a different temperature. Because at the end, I will show you that actually the final wall velocity and wall profile that you get do not depend on where the initial state on the inside the bubble is. Okay? So for the moment, let me just consider that A is here. So that's the state outside the bubble. There's some interface that you can also change, and we will see what happens if you change it. And inside the bubble, you have some other state on the lower branch. So the key point is that the pressure here is higher than the pressure here. Okay, that's the idea. And then we begin with this initial state, and we use the gravity side to evolve it. And what I'm going to show you is a movie of what the energy density as a function of Z does when you evolve in time. Okay, so that's what happens. Let's walk through the different things that we see here. First of all, this little bump here, I believe is a numerical artifact. We are still running with different resolutions, etc. So please ignore this for the moment. Okay, this is to be completely clarified. Now, what we see in this simulation that I just showed you is that the wall of the bubble here moves to the right with constant velocity, which in this case happens to be 0.236 in this particular case. we also see that even though you started with the state A outside and the state B inside, once the bubble gets in motion, the system relaxes and chooses its preferred state in front of the bubble, this D, boosted, what I'm calling D boosted here, and C inside. Okay, and this D, if you look at the fluid velocity here, it's constant and equal to 0.219. Now, these states C and D are dynamically determined in terms of the initial nucleation temperature. They don't depend on where B that you started with is, as I will show you in a second. Now, the size of this region inside the bubble and the size of this region in front of the bubble, they both grow linearly in time. However, the interface between this region and A grows a little more slowly than linearly in time. And the reason I'm saying that is just to point out that, strictly speaking, that means that even at very late times, the system is not only described by a function of z over t, because different regions grow at with different powers of t. Now, in this particular case, if you look at the speed of sound in A and the speed of sound in D, you see that they are both bigger than the wall velocity. So in this case, what this means is that what we have is a deflagration, okay, in which the bubble wall velocity is lower than the speed of sound. And note that in this model, the speed of sound is not constant. So you need to care about the speed of sound both in A and in D, okay, which are the two regions in front of the bubble. But I want to emphasize that this is just one example. You can have different wall velocities and different speeds of sound, etc., as you change the parameters, as I'm going to do in a second. But before I do that, let me just show you or convince you that indeed the wall profile becomes constant in time as it moves to the right after enough time has passed. So what I'm showing you here is a snapshot or different snapshots of the movie that I showed you. And here what I've done is I've taken these different curves and I have shifted them by a constant so you can see whether they overlap or not. And you see that the first one, which is at the earliest time, still has not converged, but then all the rest really fall on top of one another. Okay, so there's really, once you fix the nucleation temperature, there's one wall profile at late times that the system evolves to dynamically. Now, having established that the wall in the steady state does not depend on the initial conditions, let me show you that the other properties also, sorry, once you establish that it does not depend on time, so you can really talk about a single wall, let's ask whether it depends on the initial conditions. Okay? So let me show that this is not the case, again, by looking at the wall profile. So here what I'm showing you is the different profiles for the wall, again, shifted by a constant. When you start with A, so this is the energy density outside the bubble, but then you start with different states, B, B prime, or B double prime inside the bubble. So you vary B, but then the bubble will readjust itself so that inside you're always left with C, and the profile is always the same, and the wall velocity is also the same. So all I mean to say by this is that the steady state that you reach at late times does not depend on the initial conditions, just like the interface between two phase separated configurations does not depend on the initial conditions that you used to get to it. You can do a similar analysis by changing the initial conditions in the sense of not just changing B, but changing the initial wall profile that you put over here. Or you can change the initial bubble size, or you can change the initial pressure and isotropy, etc. And in all cases, you find that the final steady state is independent of these initial conditions. It only depends on the nucleation temperature. So once you fix that, then the entire late time dynamics of the bubble is always the same. Any questions?
Maybe I missed this. So when you have an anisotropic plasma, you already have two different speeds of sound in the longitudinal versus the transverse direction. How do these relate to the speeds that you have in these different phases?
Good. So let me just clarify one thing about your question, which is very pertinent, but this is not an anisotropic plasma in the sense that it's intrinsically anisotropic. It's just that you're looking at an anisotropic state because the wall is expanding in one direction and not in the others.
Mm-hmm.
Okay, but the plasma, you know, the theory is isotropic. Now, what you're asking is, of course, that once this is in motion, there will be some speed of sound in this direction and some speed of sound in that direction, so to speak. But actually, the speed of sound that I'm referring to is simply dp dE. Okay, the one that you get from the equation of state. For applied, it's just one way to define it, applied to either this point, this state here, or this state here, or this state here, or that state there. So it's simply the one you get from the corresponding equation of state at that energy density. Just to give you an idea of where the speed of sound is.
Mm-hmm. Thank you.
So for example, no problem. For example, in this case, since the system is expanding along Z, one of the things that's very relevant is what is the speed of sound right ahead of the wall, right in front of the wall. Because you want to know whether the perturbations created by the motion of the wall can propagate ahead of the wall or whether they will fall behind. And that will distinguish deflagration from detonation. Okay, so now let me address the dependence on the nucleation temperature, okay? So now let me vary the point at which you nucleate the bubble and see what happens. So first, let me just point out that these states C and D that are dynamically determined in terms of A depend relatively weakly on A. For example, here, I'm showing you three different choices for A. Here, A, A1, and A2. And all the corresponding Ds are all here, so they vary very little. And the C changes a little bit more, but not much. In contrast, the wall velocity is very sensitive to the nucleation temperature, as you might expect on general grounds, because, for example, as the nucleation temperature approaches this point, so as A approaches the turning point, so A1 is almost at the turning point, what's happening is that the pressure difference between the inside and the outside of the bubble increases. The energy density outside the bubble is going down. And also the speed of sound at this turning point is 0. Okay, so what this is doing is to increase the wall velocity. And moreover, it guarantees that it will become supersonic with respect to the speed of sound at A. Okay, because the speed of sound at A is going to 0. At this point. So in this case, what you get is a supersonic deflagration because even though the speed of the wall here, 0.29, is bigger than the speed of sound in A, which is right ahead of the wall, sorry, the speed of sound asymptotically ahead of the wall, in the region D, in between the wall and A, the speed of sound is still bigger than the speed of the wall. Okay? Now, in contrast, if you send A to this point, so if the temperature, the nucleation temperature approaches the critical temperature, then, of course, you know that if you go all the way down to TC, you expect that the wall will be at rest because then you can have phase coexistence at TC. And indeed, in that case, the pressure difference between the inside and the outside of the wall of the bubble go to 0. The energy density outside grows, so you have less force to move the medium outside, and the speed of sound simply goes to a constant here. So in that limit, what happens is that the wall velocity goes to 0, it becomes very small, and it's subsonic with respect to both A and D, as in here. Now, what about the wall profile? How does the wall profile depend on the nucleation temperature? So in principle, you could think, and it's correct, that you get a different wall profile. For example, for these three different points, A, A1, and A2, these are the three different profiles that you get. But one thing that's remarkable is that all of these profiles are given exactly by the same function up to a rescaling Okay, so there's a universal function which depends on the theory only and not on the nucleation temperature, this F, such that by a simple rescaling and a shift, it describes perfectly well all these different profiles. This I find surprising. And it points to some sort of universality of the wall profile up to these simple rescalings. Universality meaning that that is a property of the theory, just like the interface between two phases.
Can I ask?
Yes, of course. Go ahead.
In the previous slide, I thought that your late time solution here should also match with the solutions at the critical temperature in low and high energy. But it seems that you have different phase separation now.
No, you're correct. As when A2, so when this point approaches this point here, okay? Then the state inside the bubble, which is C, that I'm not showing you here, approaches this point. And the state in front of the bubble, which is D, also approaches this point. You can see this here. You see, start with A1. So for A1, the state inside the bubble is C1. And the state outside, right in front of the bubble, is D1. But now if you move A1 to A and to A2, C1 moves to C and to C2, so it's approaching this point. And D is approaching this point. So when A reaches this point, the wall velocity goes to 0. And what you have inside and outside are this and that, which is exactly what you have in a phase-separated configuration.
So, but now you have, like, depends to which combination you start, you can have different phase-separated solutions.
Why? No.
So, because, like, if you start from your A and C, right? Your final.
I don't start from A and C. I fix A. And then I choose some B, and that B will evolve dynamically to C. Okay, so let me go back here.
So
here. So you choose A here. That's the temperature at which you nucleate the bubble. Okay, and that's this energy density. And you also choose B somewhere here. You assume you nucleate a bubble with something inside. It could be the same temperature if you want. Okay, so that's your B. But then you let the system go, and this B will change dynamically to C, regardless of where B started. It doesn't matter. It will always go to the same C for a given A.
But you keep A fixed in somehow, or?
I'm only keeping A. A is only asymptotically far away from the bubble. Okay, A is, let me see if I can, A is here, far away, but once it starts going, see? So A will always be asymptotically far away, but in front of the bubble, you form D. Okay? So because of energy conservation, because you're transforming, you're starting with a higher energy here, and it's going down, so this energy has to go in front of the bubble.
So you are imposing some boundary conditions on your Z direction also?
If you want, yes, but not really. Okay, all I'm doing is preparing an initial state here. This is my initial state.
Yeah, but then I expected that you're, like, regardless of your initial configuration, as you mentioned earlier in your talk, regardless of the initial configuration, I should always settle down in a mixed state, which like in the low energy, I have the black hole.
No. This is no. That's if you. Well, okay. Yes, okay. If you, so that has to do with whether you have finite volume or infinite volume. Okay. So here, if you put this in a really, really, really big box, but finite size, okay? Once you let this go, for a long time, it will look like it's doing what I'm showing you here, okay? It will grow this region in front, you will have this thing inside, and at the very far away, you will have A, okay? Sorry. Okay, but once this bubble has expanded so far away that it reaches the end of the box, okay, it cannot keep doing this because it reaches the wall and it will bounce back. And then you will end up at asymptotically late times with a phase-separated configuration or not, depending on the average energy density between A and B. Okay? But if your box is infinite, that will never happen. This bubble will expand forever. I hope that clarifies your question. Now I understand your point.
Yeah. Thank you.
Yeah. Okay. I'm running out of time, but I'm almost done. So I just showed you that the wall profile seems to be universal, and I wanted to address the question, just like I did in the phase-separated configuration, of whether hydrodynamics describes this system. So it's well known that on general grounds, you expect hydrodynamics to describe pretty much everything but the wall profile, okay? And this is exactly what you see here. So the blue curve is the exact result coming from holography, okay? This is the wall here. The red curve is what you get with ideal hydrodynamics, and the black curve is what you get with first order hydrodynamics. And you see that first order improves a little bit the description here, but neither of these describes correctly the wall profile. Now, I believe, my intuition is that second order hydrodynamics, just like in the case of the interface, will describe the wall profile, but unfortunately I cannot show you yet because we are still computing the second order transport coefficients for this theory. But if you stay tuned, I think in a couple of weeks, this will be published and we will know. So this is just, so everything I've said so far was for planar bubbles. What I want to show you now is a movie with spherical bubbles, or more precisely, circular domains in a small box. What I mean by this is that these are not really bubbles that are going to expand, but simply two phase-separated, two phase domains, okay, at the critical temperature Tc, that have been given some initial momentum towards each other, okay, and they're going to collide and do something. And of course, they are in a small box because this was just a first simulation. So what you're going to see is finite box size effects at some point. So that's what they do. And here's where they reach the end of the box, and then everything that follows is a finite box effect. Okay, this is just to show you that we are going beyond the planar approximation, and hopefully soon we'll have more results. So any questions? Okay, so let me finish with the outlook. So let me go back to this picture that I showed you at the beginning. In the near future, or nearish future, I think we'll be able to use holography to calculate directly the gravitational wave production in a strongly coupled gauge theory with a gravity dual. What I mean by this is that all the post-nucleation dynamics is included when you read off the boundary stress tensor from the evolution of Einstein's equations here. You don't have to extract a bubble velocity or other parameters. It's all included. Once you specify the gauge theory with the gravity dual, it's all included in this stress tensor. All that dynamic is included here. Bubble expansion, bubble collisions, the effect of the sound modes, even turbulence, all of that is included. So you just take that stress tensor and you compute with that stress tensor the emission of gravitational waves in the linearized approximation, and that's the result. Thank you.
Thank you very much, David, for the very clear and interesting talk and sharing these preliminary results with us. There were a lot of questions already, but I think we have some time.
Yeah, can I ask a bit more about second order hydro?
Yes.
So you showed one slide where it worked very well and another where you were still working out the terms. So can you say a bit more about what terms are in and what terms are out and not yet in, I guess?
Yes. So let me share again. Okay. So what I wanted to emphasize was the following thing. The terms that you need to include here are the terms that include all the possible terms with purely spatial derivatives. So these are second order terms which are purely spatial in the fluid rest frame. Okay? If you think about it, that is actually the most natural definition. You can see my screen, right? Yeah. The most natural definition of what you mean by hydrodynamics as a gradient expansion, because if you are in a little fluid cell, in the rest frame of that cell, and all the spatial gradients that tell you what happens in the next cell are 0, the spatial ones, there should be no gradient corrections then, because as far as that cell is concerned, everything is homogeneous. Okay? Now, the problem with this is that if you try to use this formulation to do dynamical evolution in hydrodynamics, time evolution, you run into a problem because the theory is not causal, okay, and the time evolution problem is not well posed. So, of course, people solve that problem by using this freedom that I mentioned at the beginning in an effective theory. So what they do is they trade one of the spatial derivatives here for a time derivative, because these terms, these two spatial derivatives and this one, differ by third order and higher order terms. So at the level of effective field theory, these two are equivalent at this order. The problem, and then this one here, which is in general known as Müller-Israel-Stewart type theories, these ones give you a well-posed initial value problem, and you can do time evolution. The problem is that these two are not equivalent if the gradients are not infinitesimal, because some of the third order terms you are throwing away when you go from here to here can be large. And that's exactly the case when you're looking at a phase-separated configuration, because there all the velocities and all the time derivatives are 0. Everything is static. So this is identically 0, but this is actually large. So you're replacing something large by something that's 0. That's why it fails. So if you want to use this formulation to check if hydrodynamics works, you need to know all the coefficients that appear in this theory at second order, which are the analog of the viscosities, but there are more of them because it's second order, so there are more tensor structures you can write down. And those we already computed for this theory that I was showing you here. Okay, in this theory we computed them so we could check that in fact they give a very good description. But for this other theory that I was discussing here when I was talking about bubbles, we're in the process of finishing the calculation. So that's why I can't tell you whether second order hydro will work, but I think it will. And I think that's very nice because in many descriptions of the bubble dynamics, of course, we make good use of the fact that hydrodynamics gives a good description everywhere, except on the wall. So if we can have a better hydrodynamic theory that also describes the wall, I think that's a step forward.
Thanks.
And then we'll have to wonder whether the same is true in water.
May I ask a question? So when you say hydrodynamic evolution, you explained a little bit. I understand that you're not doing Müller-Israel-Stewart, where you basically resum all the higher contributions, including the second order, into this pi mu nu that's normally used there. So how exactly are you time evolving the system? Are you simply using the energy momentum tensor conservation equation and then saying, I have an initial profile for the fluid velocities, initial energy density, and so on, and then just evolve according to d mu f mu nu, d mu t mu nu is equal to 0?
No, actually, I'm not doing time evolution. I didn't have time to explain this. So let me show it again. So in these backup slides, I have this explicitly here. So we're not doing time evolution. We are checking the constitutive relations.
Mm-hmm.
So what we're doing is the following thing. You have an exact form of the stress tensor that comes from the gravity calculation. From that, you read off the energy density and the velocity. And then you take that and you put it in the constitutive relations for the pressures.
Mm-hmm. Understood.
Okay. And that gives you the hydro. I'm just finishing the sentence for people who may not be familiar. I know that you are. That gives you the hydrodynamic prediction for the two pressures. And then you check whether that hydro prediction for the pressures agrees with the pressures in the original stress tensor that came from gravity. So that's the comparison between this curve and any of these curves. Okay, so we're not doing time evolution. We're simply checking point by point whether the gradient expansion is a good description of the stress tensor. Whether the stress tensor can be written in a hydro form.
Thank you.
Yeah.
Are there any more questions?
Mateos,
Yeah.
can I ask you a question?
Yeah.
Okay. Hello, David. I'm David. Thanks for the very nice talk. My question is about the possible relation between your nice construction and what you already know from shock wave dynamics. To me, the motion of this, the motion of the bubble wall is similar to the motion of a shock front between upstream and downstream of flow. Then, if this analogy works, I would like to understand, would that be possible to at least as a check, use the shock wave dynamics matching conditions at the shock front, and then by using your equation of a state coming from gravity, test or find your final results in the downstream. For example, by sitting at the rest frame of shock front for a given set of initial data, we can find the downstream data. I mean, the energy profile or temperature profile on outside of the bubble. I would like to understand more about this analogy. Would that really work?
So let me first see if I'm understanding correctly what you're asking. So let me go back here, for example. So this is the wall. What these matching conditions that you're referring to, please correct me if I'm wrong, are simply the requirement that the energy flux and the momentum flux on this side match those on this side. Okay.
Exactly.
So yes, indeed, you can do that. And that will give you some constraints on, for example, what the energy density can be here related in relation to here. Okay.
Exactly, yes.
But it will not predict. So once you specify the nucleation temperature, that will allow you to determine everything else except, again, correct me if I'm wrong, except for the wall velocity. The wall velocity is still, any wall velocity is consistent with those matching conditions, okay?
Yeah.
It's just that given the wall velocity, you will get different relations between the energy density here and here, this jump, and so on. But my point is that hydrodynamics, let me go here. So hydrodynamics in this region and in this region, together with these matching conditions, is still not enough to determine the wall velocity. You still are left with this one parameter because you don't have a microscopic description of this region, because this is outside hydro.
Yeah, very good. Yes. Yes.
So I agree with you. I agree with you, and you can do everything that you were describing. Absolutely.
Yes, yes, yes. Thank you, thank you. I think one more parameter or one more piece of data is needed, and as you said, because in the vicinity of this region, in the shock front, the hydrodynamic doesn't work, and more things from microscopic theory we need.
Yes. So what I was trying to emphasize here is that these things we need from the microscopic theory may be many things, or just second order terms in hydro.
Oh, good.
So it could be that for some theories, if you know the second order coefficients, you can then use second order hydro everywhere. Okay, and then you will determine the wall velocity completely and everything else just in terms of the nucleation temperature.
Okay, very good. Thank you very much.
Yeah,
David.
I think we should close the open or the recorded session for now. We usually stick around for a little bit afterwards. So let me first thank David again and everyone for the attendance. So
thank you.